So hopefully yesterday when we were doing the powers of e, the exponential functions, you guys sort of remember that we can raise things to as a power of e. So like if I wanted to make both of these things powers of e, that would make the e to the natural log part cancel out and it would just be an x. Remember doing that yesterday? And last year in your other classes and all that stuff?
Yeah.
Yeah, all right, so that's what we're gonna do. We're gonna take y equals natural log of x, and we're going to rewrite it as e to the y equals x. And then from there, we are going to find dy dx. So we're going to take the derivative of both sides of this, and we're going to do it implicitly. So we're going to take the derivative with respect to x of e to the y, and we're going to take the derivative with respect to x of just x. Everybody good with that?
Yeah.
Okay, so if we take the derivative with respect to x of e to the y, that means we have to take the derivative of this with respect to y first. So what's the derivative of e to the y with respect to y?
Y times e to the power of y minus 1.
No. This is e to a variable, right?
It's just e to the y.
It's just e to the y, right? That's our rule from yesterday. Derivative of e to the y is e to the y. And then since we're doing it with respect to x, and we took the derivative of a y term, we have to attach a dy dx to it. Everybody okay with that?
Yes.
Okay. And then on the right-hand side, what's the derivative with respect to x of 1? Of x. Oh, it must be 1. Getting ahead of myself there, right? The derivative of x is just 1. So when we solve for dy dx, we end up with 1 over e to the y. Yeah? Easy enough?
Yes.
Yeah. So what we don't want, though, is when we started with the natural log of x, when we started with a function that was y all in terms of x, we don't want to end up with something in terms of y. So what we can do is we can just go right back up and say, well, e to the y is equal to x. And so the derivative of natural log of x equals 1 over x. Easy enough? Yeah. Cool. So that's a rule that we're going to want to memorize. Derivative of natural log is 1 over x. And if we were to make this the natural log of a function, the natural log of u, then it would just be 1 over u times the derivative of u. And so this is just the chain rule application of the derivative of natural log. Everybody okay with that?
Yep.
Okay. So if we want to find the derivative of natural log of 3x squared, that's the derivative of the natural log of u, with u equal to 3x squared. And what does that give us? Should give us 1 over u times the derivative of u, which is 6x. Or 6x over 3x squared, which simplifies to what?
2 over x.
2 over x. Perfect. One thing we might have noted is that for something like natural log of u, it's simple like this 3x squared. We could have rewritten this first if we wanted to as natural log of 3 plus the natural log of x squared. Isn't that one of your rules? One of your log rules says if you multiply inside the logarithm, you can change it to 2 logarithms that you add.
Yeah.
Okay. And so now, what's another rule with powers inside? We could always take the powers out and move them to the front. And now if I were to take the derivative of it rewritten this way, what's the derivative of natural log of 3. This is just a constant, right? So the derivative of any constant is 0. And the derivative of natural log of x is just 1 over x, and we multiply it by 2. We end up with the exact same thing that we got over here. Good or no?
Good.
All right. Any questions on that? All right, let's find the derivative of the natural log of 5 cosine 2x. How are we going to go about this?
Natural log of u when u is 5 cosine 2x.
Perfect. And all we have to do is do 1 over u for this one. And for this one, the derivative of 5 cosine 2x. That's also a chain rule problem, right? That's 5 cosine v with v equal to 2x. So the derivative of 5 cosine v will be negative 5 sine v, and then times the derivative of 2. Good so far or no? Good. And simplifying that down gives us negative 10 sine 2x over u, which was 5 cosine 2x. And we should be able to simplify that to negative 2 tangent 2x. Good or no?
Good.
All right. What if instead of it being natural log, it's a logarithm in some other base? Well, that should not make things too much more difficult. There's this formula called the change of base formula, which I found out during quarter 1 that you guys have probably mostly never heard of. Is that true?
That is correct.
That is correct. Okay, that's what I figured. So if I have something like log base 2 of 3, and I want to change this to a different base, I can change it to any base I want. Suppose we want to change it to base 10, which we normally don't write the base 10 if we're doing base 10. I just do the log base 10 of the original thing, 3, divided by the log base 10 of the original base, 2. If I want to change it to log base 7, I just change it to log base 7 of the original thing over log base 7 of the original base. Natural log is just another base, right? It's base of e for logarithm. So this is just natural log of 3 over natural log of 2. Change of base formula just says take the original thing you're taking the log of over the original base, and whatever base you want it to be, you count. Okay, pretty straightforward formula. We're not going to spend time proving it right now, but that's what it says. So it helps us to find an easy way to take the derivative of log base a of x. We just rewrite it as natural log of x over natural log of a, because we know how to take the derivative of natural log of x, right? Don't we know how to take the derivative of natural log of x already?
Yes.
Yeah. So if I rewrite it this way, 1 over the natural log of a times the natural log of x. What is 1 over the natural log of a? All right, what is a?
A constant?
It's a constant. So what's the natural log of a? Still a.
Still a. And then so it'd just be 1
Well,
over
still
a.
a. It's still a constant, right? Still a constant. And then 1 over the natural log of a is still a constant. Right, so this is all just a constant times the natural log of x. So I keep the constant. then take the derivative of the natural log of x because they're being multiplied together. So normally we would write this as 1 over x natural log of a. And that's the rule for the derivative of a logarithm in any base. It's 1 over x times the natural log of a. Fairly similar to when we did the exponential ones with a to a variable, right? Like 2 to the x or 2 to the sine x or something. Just includes that natural log in there. Everybody okay with that?
Yes.
All right. So that is third rule. No, that's the second rule we've done today, huh? That's only the second one. That's the second rule we need to know for logarithms, not the third. Why would it be a third? Could we apply the chain rule to this? Log base a of some function?
Yes.
Hopefully so, right? If I have log base a of u, right, log base a of some function, it's just 1 over that function times natural log of a, and then we got to multiply by the derivative of that function, just like we normally would with the chain rule. So that's what we've got here. We've got log base 3 of some function. So we'll write it as log base 3 of u, with u equal to 5x to the 5th power. Good or no?
Good.
All right. So the derivative of log base 3 of u, this one's derivative ought to be 1 over u times the natural log of 3. And then what should we multiply it by? 5x to the 4th, right? By the derivative of u. And if we write that all out, we got 5x to the 4th over x to the 5th, natural log of 3, when we replace the u with x to the 5th. And then we can simplify this to 5 over x ln 3. Good or no?
Good.
All right. Here's a fun one. X to the x power. So this doesn't quite follow our power rule, right? Our power rule had to be a variable to a number. True? This is a variable to a variable.
Right.
And our exponential rules had to be a number to a variable, but that's not this either. So we're going to have to use a logarithm to try to rewrite something when it's a variable to a variable or a function being raised to another function. So what we're going to do, anytime you have a function to another function, is you're going to just take the natural log of both sides of it. And that's going to allow you to rewrite the right-hand side by doing what?
Bring the x to the front.
Yeah, we're going to be able to take this exponent out to the front, and we will no longer have that problem of a variable being raised to another variable or a function being raised to another function. And how are we going to take the derivative of this now? We'll have to do it implicitly, right? So what's the derivative of natural log of y when you do it with respect to x?
One over y.
1 over y, and since we took derivative of a y term with respect to x, it needs a dy dx. And on the right-hand side, what will we do with that? How do we take this derivative?
Do we need to use the product rule?
Got to use the product rule, right? It's one function, x, times another function, natural log of x. So it'll be x times the derivative of natural log of x, which is 1 over x, 1 over x, plus natural log of x times the derivative of x, which is
1.
1. And now we have 1 over y dy dx is equal to, well, x over x is just 1, right? So 1 plus natural log of x. And we're looking for the derivative. Well, what's the derivative? The derivative is dy dx, right? So we want to solve for dy dx, giving us y times 1 plus ln x. And that's almost good enough, but the problem is that when we start with a function that's all in terms of x, we don't want to end up with any y terms in it, if we can help it. So what can I do with that y term?
Substitute.
Just substitute what y is right back in from the original, right? This becomes x to the x power times 1 plus ln x. Good or no?
Good.
Yeah.
All right, let's do another one of these. We've got a function, sine x, being raised to a variable power, sine x to the x. So we have to do what to both sides?
Take the natural log.
Take the natural log. And when we do this, when we take the natural log of both sides of something to take the derivative, we call this logarithmic differentiation. So we're going to get natural log of y equals natural log of sine x to the x. And we will take that x and pull it out in front. So natural log y equals x ln sine x. Good or no?
Good.
All right. What's the derivative of natural log of y?
1 over y dy dx.
1 over y dy dx when we do it with respect to x. And the derivative of x times the natural log of sine x has to be done with the product rule. So that'll be x. And then the derivative of natural log of sine, well, natural log of sine would be natural log of u, and u equals sine x. So that becomes 1 over u times the derivative of u, which is cosine x. And then we have to add to that the derivative of x times the natural log of sine x. And so what does dy dx equal? It equals, well, I'll bring the y over. So y times, what's x cosine x over sine x? Simplify to
X tan x.
x cotangent x. Right, yeah. And then plus our natural log of sine x. And we need to replace the y with sine x to the x. So we end up with a final answer of sine x to the x times x cotangent x plus natural log sine x. Good or no?
Good.
Spectacular. All right. We're going to, everybody feel like they could do simple problems like those ones? Nothing too crazy?
Yes.
All right, good. You're all familiar with inverse trig functions, I hope? Yeah? Inverse sine, inverse cosine, inverse tangent.
Yeah.
Yeah? Okay, so the inverse trig function just allows you to put in a value and get out an angle from it. So for inverse sine has a domain from -1 to 1, and it has a range from -π/2 to π/2. So whenever you plug in a number to inverse sine, you always get out an angle that's in the first or the fourth quadrant, that's between -π/2 and π/2. So that's an important thing for us to sort of remember as we go forward in the class, that you can only plug in numbers between -1 and 1, and you only get out angles in the first or the fourth quadrant. Hopefully you recognize that these two things mean the same thing. That if I have the function y equals inverse sine of x, I could take the not take the derivative, but I could take the sine of both sides of this. And what would happen to the sine of the inverse sine? Sine and the inverse sine things are opposite operations of each other, and we'd end up with sine of y is just equal to x, right? So these two things are equivalent. Good or no?
Good.
Okay. So in order to find the derivative of inverse sine of x, to find dy dx for it, we're going to use this form and we're going to differentiate it implicitly. So if we differentiate the left-hand side with respect to x, and we differentiate the right-hand side with respect to x, what do we get on each side? On the left, we should get
1.
and on the right, we should get what's the derivative of sine y?
Cosine y dy dx.
Cosine y dy dx. So what does dy dx equal? It equals 1 over cosine y. Yeah? Everybody agree with that?
Yes.
Okay. Well, we started with y equals the inverse sine of x, right? We started with everything in terms of x. So we'd like to get this back to have everything in terms of x. So how are we going to do that? If dy dx equals 1 over cosine y with x equal to sine y, there's two good ways to go about putting this in terms of x. Anybody see one of those weird ways?
Wait, isn't it negative sine y?
Cosine?
Yeah.
No, cosine y does not equal negative. I mean, the derivative of cosine y is negative sine.
Oh, yeah.
We've already found the derivative. We're just trying to equate cosine y into something in terms of x.
Would you take the inverse cosine of it?
That's a good idea, but we can't just take the inverse cosine of this without doing that to the other side also, and that's going to be a little bit of a problem. Tell me about this x equals sine y. How do you usually deal with trig functions like sine of an angle? Where do you usually see those? Or where did you first in your life see them?
Triangles?
Triangles, specifically right triangles? Yeah?
Yeah.
Well, here's an angle, y. What's the sine of y? What does that mean in a right triangle? It means which side? Opposite over hypotenuse, right? Well, what is the sine of y equal? It equals x. X is just x over 1, right? So that should be opposite over hypotenuse. True?
True.
Using the Pythagorean theorem, what does the third side become? One squared equals x squared plus, I don't know, whatever this thing is, we'll call it a. What does a equal?
Cosine y.
Well, it does equal cosine y, but I just meant in terms of the Pythagorean theorem that we used here.
1 squared minus x squared, or the square root of 1 minus x
Square root of 1 minus x squared,
squared.
right? So this is square root 1 minus x squared, and cosine of y ought to be that square root of 1 minus x squared over 1. So we really just have 1 over root 1 minus x squared. And this right here is the derivative of the inverse sine. Good or no? Everybody see how we got to that or no?
So y is equal to the inverse sine of x. Is the derivative of that function is what we just found?
That's correct, right? We started here with y equals inverse sine of x, turned it into x equals sine of y, which was equivalent. So the dy dx for this should be the same as the dy dx for this. Found the dy dx to be 1 over cosine y. Went over here and said, well, if that's true and this is true, because this is what we started with, x is sine y, we can find what cosine y is using a right triangle and plug it in. Pretty cool, huh?
Wonderful.
Yeah, it is pretty cool. Yeah. So you can find the derivatives of the other 5 inverse trig functions in a very, very similar manner. And we can also apply the chain rule to each of them. We're going to skip that page. This is the derivatives of all 6 of the inverse trig functions. We're not going to go through and prove all of them, although you're going to want to know them all. And these are all the chain rule applications of them. So if I have inverse sine of a function, it's 1 over the square root of 1 minus the function squared times the derivative of the function. This is the one we just proved. Okay. The inverse cosine just has a negative in front of it. Otherwise, it's the same. Inverse tangent, which shows up very often, is just 1 over 1 plus u squared times the derivative of u. And the inverse cotangent just throws a negative in front of it. And then secant and cosecant are these two. And we'll note that sine and cosine are the same, except that the cosine has a negative in front of it. And that tangent and cotangent are the same, except that the cotangent has a negative in front of it. And same with secant and cosecant, they're the same, except that the cosecant has a negative in front of it. So should be easy to remember those 6, hopefully. And you're going to need to know all 6 of those also. Good or no?
Good enough.
Good enough. That's not a resounding something or another. I don't know. Not a resounding support of understanding what we're doing. We're going to have to go through this again when we come back from Thanksgiving, I think, a little bit and practice some more of these, but that's okay. So let's just do a couple of these here and see if we can sort of get the idea. We want to find the inverse sine of root x. And I'm just going to give us a new page for this. Inverse sine of root s. So it's the inverse sine of u, isn't it? With u equal to root x. Everybody agree with that?
Yes.
All right, and what should our derivatives be then? The derivative with respect to u of y, dy du, is just 1 over root 1 minus u squared, and then we got to multiply it by the derivative of u. And what's the derivative of u?
1 over 2 root x.
1 over 2 root x. So we're just going to multiply these things together. Gives us a 1 over a square root of 1 minus, and u was root x, so root x squared, and then times 2 root x. And if we simplify that down, what do we get? We get 1 over 2. We got a square root of 1 minus x now, right? If we square that root x, and then another root x down there. Good or no?
Good.
All right, let's do inverse tangent of x squared. So using the chain rule, this becomes y equals the inverse tangent of u with u equal to x squared. And from our formulas, what's the derivative of the inverse tangent of u?
One over 1 plus u squared times the derivative of u.
So 1 over 1 plus u squared times 2x, or just 2x over 1 plus x squared squared, or 2x over 1 plus x to the 4th. Good or no?
Good.
All right. We got time for one more here, maybe. How about inverse secant of square root of x squared minus 1? This one is a chain rule within the chain rule. So we've got y equals inverse secant u with u equal to root x squared minus 1. Inverse secant of u, that one looks like what? One over the absolute value of u times the square root of u squared minus 1, right? And then we need to multiply that by the derivative of u, which is the square root of v, with v equal to x squared minus 1. So what's the square root of v's derivative?
1 over 2 root v.
1 over 2 root v. And what's the derivative of v? It should be 2x. Now we'll just substitute everything and cancel some like terms. So cancel the 2's. And if we plug it all in, we should get x over the absolute value of the square root of x squared minus 1 times the square root of x squared minus, or of the square root of x squared minus 1 squared minus 1 times the square root of x squared minus 1. Everybody agree with that? Just replacing the u's with root x squared minus 1s and the v's with x squared minus 1s. Yeah, no, maybe?
Yeah.
Okay. Absolute value of a square root of something is just kind of redundant, right? The square root's always positive, so the absolute value doesn't mean anything. And I've got a square root of x squared minus 1 times a square root of x squared minus 1, which ought to be just x squared minus 1. And then what's inside this square root here? Square root of x squared minus 1 squared is just x squared minus 1, minus another one is x squared minus 2. Good or no?